Imagine a cosmic vacuum cleaner, so powerful it can swallow entire stars, yet it's not indestructible. In fact, it's slowly fading away, and the culprit is something so tiny, it's almost invisible. This isn't science fiction, it's the reality of black holes and the mind-blowing phenomenon known as Hawking radiation. Stick around, because we're about to dive into a story of cosmic cataclysms, quantum whispers, and the ultimate showdown between gravity and the tiniest particles in the universe. You won't want to miss this, because it's not just about the death of black holes. It's about the very fabric of reality. The nature of black holes. Black holes are regions in space where gravity is so strong that nothing, not even light, can escape. They form when massive stars collapse under their own gravity, creating a singularity, a point of infinite density, surrounded by an event horizon, a boundary beyond which nothing can return. The nature of black holes is quite fascinating. They warp space-time, the fabric of the universe, and their immense gravitational pull affects everything around them. Despite their name, black holes aren't empty. They are dense and contain a tremendous amount of mass packed into a very small space. At the heart of a black hole lies the singularity, a point where the laws of physics as we know them break down. Surrounding this singularity is the event horizon, a boundary where the escape velocity exceeds the speed of light. This means that once anything crosses this horizon, it is inexorably pulled towards the singularity. The event horizon is not a physical surface but a point of no return, a boundary in space-time. Black holes come in various sizes, from stellar mass black holes, which are a few times the mass of the Sun, to supermassive black holes, which can be billions of times more massive. These cosmic giants play a crucial role in the evolution of galaxies, influencing star formation and galactic structure. Now, let's talk about Hawking radiation. Proposed by physicist Stephen Hawking, this theory suggests that black holes aren't entirely black. Instead, they emit radiation due to quantum effects near the event horizon. This radiation is a result of particle-antiparticle pairs being created near the black hole's boundary. Normally, these pairs annihilate each other, but near the event horizon, one particle can fall into the black hole while the other escapes. The escaping particle is what we perceive as Hawking radiation. Over time, this process causes the black hole to lose mass and energy, leading to its gradual evaporation. It's like a black hole slowly melting away, particle by particle. The gradual evaporation of black holes due to Hawking radiation is a slow process. For a stellar mass black hole, it would take much longer than the current age of the universe to evaporate completely. However, smaller black holes, if they exist, would evaporate more quickly. As a black hole loses mass, its temperature increases, and the rate of evaporation accelerates. Eventually, the black hole would reach a point where it explodes in a final burst of gamma rays. This process is so slow that it's not something we can observe directly, but it's a fascinating theoretical prediction that bridges the gap between quantum mechanics and general relativity. Gravitational singularity. At the heart of a black hole lies a gravitational singularity, a point where the laws of physics as we know them break down. This singularity is a region of infinite density and curvature where all the mass of the black hole is concentrated into an infinitely small point. It's like trying to squeeze an entire star into a space smaller than an atom. Around this singularity, the gravitational pull is so strong that not even light can escape, hence the term black hole. The singularity itself is hidden behind the event horizon, a boundary from which nothing can return. Now, let's talk about Hawking radiation and how it leads to the eventual death of black holes. In the 1970s, physicist Stephen Hawking proposed that black holes aren't entirely black. Instead, they emit radiation due to quantum effects near the event horizon. To understand this, picture the vacuum of space as a seething foam of virtual particles and antiparticles, constantly popping in and out of existence. These pairs usually annihilate each other almost instantly. However, near the event horizon, one particle can fall into the black hole while its antiparticle escapes. From an outside observer's perspective, this escaping particle is seen as Hawking radiation. Over time, the emission of Hawking radiation causes the black hole to lose mass. It's like a slow, cosmic evaporation process. As the black hole loses mass, its event horizon shrinks, and the gravitational pull weakens. This process is incredibly slow for large black holes, taking much longer than the current age of the universe. But for smaller black holes, the evaporation happens faster. Eventually, the black hole will lose so much mass that it explodes in a final burst of gamma rays, marking the end of its life. The gravitational singularity, once hidden behind the event horizon, is no more. The entire process is a fascinating dance of quantum mechanics and general relativity, showcasing the intricate and often counterintuitive nature of our universe. Event horizon. The event horizon of a black hole is a boundary, a point of no return. Think of it as the edge of a cosmic waterfall. Once something crosses this boundary, it's pulled inescapably towards the singularity at the center of the black hole. Light, too, is affected by this intense gravity, which is why black holes are, well, black. They don't emit light, they trap it. This boundary isn't a physical surface, but a region in space where the gravitational pull becomes so strong that escape becomes impossible. Now, let's talk about Hawking radiation. In the quantum world, particle-antiparticle pairs are constantly popping in and out of existence. It's like a bustling marketplace where particles appear and disappear in the blink of an eye. Near the event horizon, one of these particles might fall into the black hole while its partner escapes. The escaped particle becomes what we call Hawking radiation. The black hole loses a tiny bit of mass in this process. It's like a black hole is slowly sweating away its existence. Over time, this process causes the black hole to shrink. It's a slow, gradual evaporation. For a black hole with the mass of our Sun, this would take an unimaginably long time, much longer than the current age of the universe. But given enough time, even the most massive black holes would evaporate completely. This is because the smaller the black hole, the faster it evaporates. It's a runaway process. The end result is a spectacular explosion of energy and particles, marking the death of the black hole. But what happens at the event horizon during this process? As the black hole loses mass, the event horizon shrinks. The boundary of no return gets smaller and smaller. Eventually, it disappears entirely, leaving behind only a burst of energy and particles. This is the final act in the life of a black hole, a dramatic end to a cosmic giant. It's a reminder that even the most powerful and seemingly eternal objects in the universe have a lifespan. They are born, they live, and they die. Escape velocity and black holes. Escape velocity is the speed an object needs to break free from a planet or other celestial body's gravitational pull. For Earth, it's about 11.2 kilometers per second. But for black holes, escape velocity exceeds the speed of light. Since nothing can surpass this cosmic speed limit, anything crossing a black hole's event horizon is trapped forever. This is why black holes are infamous for their insatiable appetite and inescapable grasp. Now, let's talk about particle-antiparticle pairs. In the quantum world, these pairs pop in and exist near the event horizon. Think of them as tiny, ephemeral couples holding hands briefly before parting ways. Normally, they annihilate each other, vanishing without a trace. But near a black hole's intense gravitational field, one partner might fall in while the other escapes. The escaped particle is what we call Hawking radiation. It's like a tiny, lucky soul breaking free from a cosmic prison, leaving its partner behind. Over time, these escaping particles steal energy from the black hole. It's a slow, gradual process, like a leaky bucket losing water drop by drop. This causes the black hole to lose mass and shrink. Eventually, after an unimaginably long time, the black hole could evaporate completely. This is the essence of black hole evaporation, a theoretical process proposed by Stephen Hawking. It's a slow fade into nothingness, a cosmic whisper of entropy and decay. Yet, it's a reminder that even the most formidable cosmic entities aren't eternal. They, too, must face their end. Quantum mechanics basics. Quantum mechanics, the branch of physics that deals with the smallest particles in the universe, introduces some mind-bending concepts. At its core, it suggests that particles can behave as both particles and waves, a property known as wave-particle duality. This is quite different from the everyday objects we interact with, which follow classical physics. In the quantum world, particles can exist in multiple states or places at once, a condition described by the wave function. It's only when we measure or observe these particles that they choose a definite state. This is what makes quantum mechanics so fascinating and, at times, counterintuitive. One of the most intriguing phenomena in quantum mechanics is the creation of particle-antiparticle pairs. In the vacuum of space, which isn't truly empty but filled with quantum fluctuations, energy can briefly convert into matter. This happens due to the uncertainty principle, which allows for temporary violations of the conservation of energy. A particle and its antiparticle, a particle with the same mass but opposite charge, can pop into existence, borrow energy from the vacuum, and then annihilate each other, returning that energy to the vacuum. It's like a tiny, ephemeral loan of energy from the universe, with no net cost. This process is constant and happens everywhere, even in the vast emptiness of space. Now, let's bring black holes into the picture. Black holes are regions in space where the gravitational pull is so strong that nothing, not even light, can escape. They form when massive stars collapse under their own gravity. But what happens when quantum mechanics meets black holes? This is where Hawking radiation comes into play. Near the event horizon of a black hole, the point of no return, the creation of particle-antiparticle pairs takes on a dramatic twist. One particle can fall into the black hole while its antiparticle escapes. The escaped particle becomes what we call Hawking radiation. From the outside, it looks like the black hole is emitting radiation, causing it to lose mass over time. It's as if the black hole is slowly evaporating, losing energy and mass in the process. This gradual loss of mass is what leads to the eventual death of black holes. Over an incredibly long period, the black hole will lose all its mass and energy through Hawking radiation, leaving behind only empty space. The exact details of what happens at the very end are still a topic of ongoing research and debate. Some theories suggest that the black hole might evaporate completely, while others propose that it might leave behind a tiny, stable remnant. Regardless, the idea that black holes can die is a profound consequence of the interplay between quantum mechanics and general relativity. It challenges our understanding of the universe and pushes the boundaries of our knowledge. Uncertainty principle. In the vast, mysterious expanse of the cosmos, black holes are among the most enigmatic entities. These celestial objects, born from the remnants of massive stars, possess a gravitational pull so strong that not even light can escape their grasp. Yet, despite their fearsome reputation, black holes aren't entirely invincible. In fact, they are slowly evaporating, a phenomenon attributed to something called Hawking radiation. At the heart of this process lies the uncertainty principle, a fundamental concept in quantum mechanics. The uncertainty principle, formulated by Werner Heisenberg, states that it's impossible to simultaneously know certain pairs of properties of a particle, such as its position and momentum, with perfect accuracy. This isn't a statement about our measurement capabilities, but a fundamental property of the universe. In the context of black holes, this principle leads to a fascinating and counterintuitive consequence. Near the event horizon, the boundary beyond which nothing can escape a black hole, the vacuum of space isn't entirely empty. Instead, it's a seething foam of particle-antiparticle pairs that constantly pop in and out of existence. These pairs, often referred to as virtual particles, are a direct result of the uncertainty principle. Now, picture this. A pair of virtual particles pops into existence near the event horizon. One particle falls into the black hole, while its antiparticle partner escapes into space. From a distance, it might seem like the black hole has emitted a particle, which is essentially what Hawking radiation is. However, the story doesn't end there. The particle that fell into the black hole carries a negative energy, effectively reducing the black hole's mass. Over time, this process repeats itself countless times, leading to a gradual evaporation of the black hole. It's like a cosmic version of a slow leak, where the black hole loses a tiny bit of its mass each time a particle-antiparticle pair is created near its event horizon. This process, although incredibly slow, has profound implications. For instance, it sets a finite lifespan for black holes. Given enough time, they will evaporate completely, leaving behind only Hawking radiation. Moreover, This phenomenon bridges the gap between two seemingly incompatible theories: general relativity, which governs the macroscopic world, and quantum mechanics, which rules the microscopic realm. It's a testament to the intricate and interconnected nature of the universe, where the tiniest fluctuations can have monumental consequences. Particle-antiparticle pairs. In the vast, mysterious expanse of the universe, black holes are among the most enigmatic objects. They are regions of space where gravity is so strong that nothing, not even light, can escape. But what happens to these cosmic giants over time? Enter Hawking radiation and the fascinating concept of particle-antiparticle pairs. At the edge of a black hole, known as the event horizon, the fabric of space-time is warped to an extreme degree. This intense gravitational field can give rise to a peculiar quantum phenomenon. Particle-antiparticle pairs are created from the vacuum of space, a process driven by the uncertainty principle. These pairs usually annihilate each other almost instantly, but near a black hole, one particle can fall in while the other escapes. This escaping particle is what we call Hawking radiation. Think of it like a cosmic tug-of-war. The particle that falls into the black hole reduces its mass slightly, while the one that escapes carries away energy. Over time, this process causes the black hole to lose mass and energy, gradually causing it to shrink. It's as if the black hole is slowly evaporating, a concept first proposed by physicist Stephen Hawking. The particle-antiparticle pairs are like tiny, invisible workers chipping away at the black hole's immense structure. This evaporation process is incredibly slow for large black holes, but over billions of years, it can lead to their complete demise. The smaller the black hole, the faster it evaporates. For instance, a black hole with the mass of a mountain would evaporate in a burst of gamma rays within a human lifetime. The creation of particle-antiparticle pairs is a fundamental aspect of quantum field theory. In the quantum world, particles and antiparticles are constantly popping in and out of existence, borrowing energy from the vacuum for a fleeting moment. This is a bit like taking out a very short-term loan from the universe. Normally, these pairs annihilate each other almost immediately, returning the borrowed energy. However, near the event horizon of a black hole, the intense gravitational field can separate the pairs. One particle falls into the black hole, while the other escapes as Hawking radiation. This process not only leads to the gradual evaporation of black holes, but also provides a mechanism for black holes to emit energy and lose mass. The implications of this phenomenon are profound. It suggests that black holes are not entirely black, but emit radiation and can eventually disappear. This challenges the classical notion of black holes as eternal, unchanging objects. The particle-antiparticle pairs play a crucial role in this process, acting as the mediators of the black hole's slow demise. As the black hole loses mass, it becomes hotter and emits more radiation, accelerating the evaporation process. This feedback loop continues until the black hole reaches a point where it can no longer sustain the creation of particle-antiparticle pairs. At this stage, the black hole disappears in a final burst of energy, leaving behind a slightly warmer and more chaotic universe. Virtual particles in a vacuum. In the vast, seemingly empty expanse of space, a fascinating dance of particles and antiparticles occurs constantly. This phenomenon, known as quantum fluctuation, is a fundamental aspect of quantum field theory. Even in a vacuum, where one might expect absolute nothingness, pairs of particles and their antiparticles pop into existence, borrow energy from the vacuum, and then annihilate each other in a fleeting instant. These ephemeral entities are called virtual particles, and their existence is a direct consequence of the Heisenberg uncertainty principle, which allows for temporary violations of the conservation of energy. Now, picture a black hole, a region of space where gravity is so intense that nothing, not even light, can escape. According to Stephen Hawking's groundbreaking theory, these virtual particles play a crucial role in the behavior of black holes. When a pair of virtual particles forms near the event horizon, the point of no return around a black hole, one particle might fall into the black hole while its partner escapes into space. The particle that escapes becomes real, stealing energy from the black hole in the process. This phenomenon is known as Hawking radiation. Over time, this process causes the black hole to lose mass and energy. It's as if the black hole is slowly evaporating, with the virtual particles acting like tiny, persistent thieves siphoning off its energy. The rate of this evaporation is incredibly slow for large black holes, but for smaller ones, it can be significant. Eventually, if a black hole loses enough mass, it could theoretically evaporate completely, leaving behind only a burst of Hawking radiation. This gradual disappearance of black holes due to quantum effects is a mind-bending consequence of the interplay between quantum mechanics and general relativity. Hawking's groundbreaking theory. In the vast expanse of the cosmos, black holes are among the most enigmatic and powerful objects. They are regions of space where gravity is so strong that nothing, not even light, can escape. For decades, they were thought to be eternal, unchanging entities. However, Stephen Hawking's groundbreaking theory challenged this notion, introducing the concept of black hole evaporation and the emission of what is now known as Hawking radiation. At the heart of Hawking's theory lies the peculiar behavior of quantum particles in the vacuum of space. According to quantum mechanics, the vacuum is not truly empty, but teeming with particle-antiparticle pairs that pop in and out of existence in a fleeting dance. These pairs, often referred to as virtual particles, usually annihilate each other almost instantaneously. However, near the event horizon of a black hole, the immense gravitational pull can tear these pairs apart. One particle might fall into the black hole, while its antiparticle escapes into space. From an outside observer's perspective, it appears as if the black hole is emitting radiation, which we now call Hawking radiation. This process might seem innocuous at first, but it has profound implications. Each time a particle escapes, the black hole loses a tiny amount of its mass. Over inconceivably long periods, this gradual loss of mass leads to the black hole shrinking and eventually evaporating completely. It's akin to a massive iceberg slowly melting under the warmth of the sun, except the sun, in this case, is the quantum vacuum itself. The smaller the black hole, the faster it evaporates. This is because the temperature of the Hawking radiation increases as the black hole's mass decreases, leading to a runaway process. In the final stages, the black hole might explode in a spectacular burst of energy, releasing the last remnants of its mass in a fiery finale. The implications of Hawking radiation extend beyond the fate of black holes. It bridges the gap between quantum mechanics and general relativity, two pillars of modern physics that have long been at odds. By showing that black holes can emit radiation and eventually evaporate, Hawking's theory provides a glimpse into the fundamental nature of the universe. It challenges our understanding of entropy, information, and the very fabric of spacetime. Moreover, it raises profound questions about the ultimate fate of the cosmos. If black holes can evaporate, what does this mean for the long-term stability of the universe? These are questions that continue to puzzle and inspire physicists today, driving the quest for a deeper understanding of the cosmos. Black hole thermodynamics. Black holes, those cosmic enigmas with gravitational pulls so strong that not even light can escape, have long been thought of as eternal and unchanging. However, the discovery of Hawking radiation has turned this idea on its head. Proposed by physicist Stephen Hawking, this theory suggests that black holes can slowly lose mass and energy over time, eventually evaporating completely. This process is deeply tied to the fascinating field of black hole thermodynamics, which draws parallels between the behavior of black holes and the laws of thermodynamics that govern everyday physics. At the heart of this theory lies the quantum mechanical phenomenon of particle-antiparticle pair creation. In the vast emptiness of space, quantum fluctuations can cause pairs of particles and their antiparticles to pop into existence briefly before annihilating each other. Near the event horizon of a black hole, one of these particles can be sucked in while its partner escapes. The escaped particle becomes what we call Hawking radiation. This process might seem like a tiny, almost insignificant event, but over vast cosmic timescales, it leads to a significant loss of mass for the black hole. Think of it like a slow, steady leak from an otherwise impenetrable container. The black hole is slowly losing its contents without any obvious way to replenish them. The gradual evaporation of black holes through Hawking radiation is a slow process. For a black hole with the mass of the Sun, it would take an unimaginably long time, far longer than the current age of the universe, to evaporate completely. However, smaller black holes, if they exist, would evaporate much faster. This evaporation process is governed by the principles of black hole thermodynamics, which include analogs to the laws of thermodynamics. For instance, the area of the event horizon of a black hole can be thought of as analogous to entropy in a thermodynamic system. As the black hole loses mass, its event horizon shrinks, much like how a system loses entropy as it cools down. The implications of black hole thermodynamics are profound. They challenge our understanding of gravity, quantum mechanics, and the nature of information itself. One of the most intriguing questions is what happens to the information that falls into a black hole. According to the laws of physics, information cannot be destroyed, but if a black hole evaporates completely, where does the information go? This is known as the black hole information paradox, and it remains one of the most pressing questions in theoretical physics. The study of black hole thermodynamics continues to push the boundaries of our knowledge, offering glimpses into the fundamental workings of the universe. Hawking radiation discovery. In the vast, mysterious expanse of the cosmos, black holes have long been considered regions of eternal darkness, where nothing, not even light, can escape. However, the discovery of Hawking radiation challenged this notion, introducing the idea that black holes can slowly lose mass and energy over time, eventually leading to their evaporation. This groundbreaking concept was proposed by physicist Stephen Hawking, who suggested that quantum effects near the event horizon of a black hole could lead to the emission of radiation. At the heart of this phenomenon lies the creation of particle-antiparticle pairs near the event horizon. In the quantum world, these pairs are constantly popping in and out of existence, a fleeting dance of matter and antimatter. Normally, these pairs annihilate each other almost instantaneously. However, near the event horizon, the intense gravitational field can tear these pairs apart before they have a chance to recombine. One particle falls into the black hole, while the other escapes as Hawking radiation. This process is akin to a cosmic game of tug-of-war, where the black hole's gravity and the quantum vacuum are the opposing forces. The escaping particle carries away a tiny amount of the black hole's energy, causing it to lose mass over time. This gradual loss of mass is what leads to the eventual evaporation of black holes. It's a slow, inexorable process, much like a candle burning down to its wick. For a black hole with the mass of the Sun, this process would take an astonishingly long time, far longer than the current age of the universe. However, for smaller black holes, the evaporation process could be much faster. This discovery has profound implications for our understanding of black holes and the universe as a whole. It suggests that black holes are not eternal prisons for matter and energy, but rather, they are dynamic objects that can evolve and eventually disappear. Energy conservation and Hawking radiation. In the vast cosmos, black holes are among the most enigmatic and powerful objects, exerting a gravitational pull so strong that not even light can escape. Yet, they are not entirely invincible. Stephen Hawking proposed a groundbreaking theory suggesting that black holes can slowly evaporate over time, emitting radiation in a process now known as Hawking radiation. This phenomenon is a direct consequence of quantum mechanics and general relativity working together in the extreme environment near a black hole's event horizon. At the heart of this process lies the creation of particle-antiparticle pairs, a common occurrence in the quantum foam of empty space. These pairs usually annihilate almost instantly, but near the event horizon, one particle can fall into the black hole while the other escapes as radiation. This escapee is what we observe as Hawking radiation. The creation of these particle pairs is a bit like a cosmic game of chance. Think of it as a bustling marketplace where pairs of particles are constantly being created and destroyed. Most of the time, they meet and cancel each other out, like friends who bump into each other and go their separate ways. However, near the event horizon, the immense gravitational pull can separate the pair. One particle gets sucked into the black hole, while the other escapes into space. This escaping particle carries away energy, which is crucial for understanding energy conservation in this process. The energy for the escaping particle comes from the black hole itself, causing the black hole to lose mass over time. It's as if the black hole is slowly paying for the energy of the escaping particle with its own mass. Energy conservation is a fundamental principle in physics, stating that energy cannot be created or destroyed, only transferred or transformed. In the context of Hawking radiation, this principle holds true, but in a somewhat counterintuitive way. The energy of the escaping particle is balanced by the decrease in the black hole's mass. As the black hole loses mass, its gravitational pull weakens, and it slowly evaporates. This process is incredibly slow for large black holes, taking longer than the current age of the universe for a black hole with the mass of our Sun to evaporate completely. However, for smaller black holes, the evaporation process can be much faster. The final stages of this evaporation are particularly interesting, as the black hole becomes smaller and hotter, emitting more intense radiation until it finally disappears in a burst of energy. The implications of Hawking radiation and the eventual death of black holes are profound. It challenges our understanding of black holes as eternal, unchanging objects and introduces the concept of black hole thermodynamics. This includes the idea that black holes have a temperature and entropy, much like ordinary thermodynamic systems. The temperature of a black hole is inversely proportional to its mass, meaning smaller black holes are hotter. As they lose mass through Hawking radiation, they become hotter and evaporate faster. This positive feedback loop leads to the eventual complete evaporation of the black hole. The end result is a universe where black holes, once thought to be indestructible, can slowly fade away, leaving behind only radiation. This process underscores the deep connection between quantum mechanics and gravity, two pillars of modern physics that are still not fully reconciled. Black hole evaporation process. Black holes, those cosmic vacuum cleaners, aren't as eternal as once thought. They can shrink and vanish, a process known as black hole evaporation. This mind-bending idea comes from Stephen Hawking's groundbreaking work. He proposed that black holes aren't entirely black. They emit radiation, now famously called Hawking radiation. This radiation is incredibly faint, but over time, it causes black holes to lose mass and eventually disappear. Picture this. The universe is a bustling quantum foam where particle-antiparticle pairs pop in and out of existence all the time. It's like a lively party where guests, particles, and their twins, antiparticles, constantly appear and disappear. Near a black hole's event horizon, the boundary beyond which nothing can escape, something peculiar happens. One of these particle pairs can get separated by the black hole's immense gravity. One particle falls in, while the other escapes. The escaped particle is what we detect as Hawking radiation. The infalling particle causes the black hole to lose a tiny bit of mass. It's like the black hole is slowly paying a price for its existence. This process is incredibly slow. For a black hole with the mass of our Sun, it would take around 10⁻⁶7 years to evaporate completely. That's a number so large, it's practically impossible to comprehend. But for smaller black holes, the process is much faster. A black hole with the mass of a mountain, for instance, would evaporate in about 265 million years. As the black hole loses mass, the rate of evaporation increases. Towards the end, the black hole would emit more and more radiation, culminating in a dramatic explosion. This final burst of energy is one of the most energetic events in the universe, second only to the Big Bang itself. The evaporation of black holes has profound implications for our understanding of the universe. It suggests that black holes aren't eternal, but rather, they have a lifespan. This challenges our notions of time and entropy. Moreover, it raises questions about what happens to the information that falls into a black hole. This is known as the black hole information paradox, a hot topic in theoretical physics. Despite decades of research, it remains one of the biggest mysteries in the universe. The evaporation of black holes is a reminder that the cosmos is full of surprises, and our understanding of it is far from complete. Stefan Boltzmann law application. Black holes, those cosmic vacuum cleaners, aren't as eternal as once thought. They can evaporate, and the Stefan Boltzmann law plays a crucial role in this process. This law, which describes the total energy radiated per unit surface area of a black body in terms of its temperature, is key to understanding how black holes lose mass over time. In the context of black holes, this radiation is known as Hawking radiation, named after the physicist Stephen Hawking, who theorized its existence. Picture this. Near the event horizon of a black hole, particle-antiparticle pairs are constantly being created and annihilated. This is a quantum effect, a reminder that empty space isn't truly empty. Sometimes, one of these particles falls into the black hole while its partner escapes. From an outside observer's perspective, it looks like the black hole is emitting radiation. The Stefan-Boltzmann law helps us calculate the rate of this energy loss. The law states that the power radiated per unit area is proportional to the fourth power of the temperature. For a black hole, the temperature is inversely proportional to its mass. So, as a black hole loses mass, its temperature increases, and it radiates even more intensely. This process is incredibly slow for large black holes. A black hole with the mass of our Sun would take longer than the current age of the universe to evaporate completely. But for smaller black holes, this process can be much faster. As the black hole loses mass, its event horizon shrinks, and the rate of radiation increases. It's a runaway process. The black hole's death throes are spectacular, with a final burst of gamma rays as the last of its energy is released. The Stefan-Boltzmann law, in this context, is a tool to quantify this dramatic end. It's a reminder that even the most formidable cosmic objects are not immune to the laws of thermodynamics. Black hole lifespan. Black holes, those cosmic vacuum cleaners, are not as eternal as once thought. They have a lifespan, a beginning, and an end, thanks to a mind-bending phenomenon called Hawking radiation. Picture a black hole as a cosmic ice cube. Just as an ice cube doesn't last forever, neither does a black hole. It slowly shrinks and eventually vanishes, but the process takes an incredibly long time. At the heart of this process is a peculiar quantum mechanical trick: particle-antiparticle pairs popping in and out of existence near the event horizon, the black hole's point of no return. Think of it like a bustling marketplace where pairs of particles appear, usually annihilating each other almost instantly. But near a black hole's edge, one particle might fall in while its partner escapes. The escaping particle becomes what we call Hawking radiation. The black hole loses a tiny bit of mass each time this happens. It's like the black hole is slowly leaking energy, a cosmic version of a slow drip from a faucet. The rate of this evaporation is incredibly slow for large black holes. A black hole with the mass of our Sun would take about 10^67 years to evaporate completely. That's a number so large it's almost impossible to comprehend. But for smaller black holes, the process is much faster. A black hole with the mass of a mountain, for instance, would evaporate in a mere 265 million years. As the black hole loses mass, the rate of evaporation increases, leading to a final explosive burst of gamma rays. This is the black hole's last hurrah before it disappears entirely. The concept of black hole evaporation is a remarkable prediction of theoretical physics. It bridges the gap between quantum mechanics and general relativity, two pillars of modern physics that are notoriously difficult to reconcile. Hawking radiation provides a glimpse into the quantum nature of black holes, revealing that they are not the eternal prisons of the universe once thought. Instead, they are dynamic, evolving objects with a finite lifespan. This understanding has profound implications for our comprehension of the universe, from the behavior of black holes to the nature of information and entropy. It's a testament to the power of human curiosity and the relentless pursuit of knowledge. Information paradox. Black holes are among the most enigmatic objects in the universe, and their behavior continues to baffle scientists. One of the most intriguing phenomena associated with black holes is Hawking radiation, a theoretical process by which black holes can emit particles and gradually lose mass. This process was proposed by physicist Stephen Hawking in the 1970s and has profound implications for our understanding of black holes and the fundamental laws of physics. At the heart of this phenomenon lies the information paradox, a puzzle that challenges our current understanding of quantum mechanics and general relativity. Hawking radiation arises from the quantum mechanical effects near the event horizon of a black hole. In the void of space, particle-antiparticle pairs are constantly being created and annihilated in a process known as vacuum fluctuation. Normally, these pairs annihilate each other almost instantaneously. However, near the event horizon of a black hole, one of the particles can fall into the black hole while the other escapes as Hawking radiation. This escaping particle carries away a tiny amount of the black hole's energy, causing the black hole to lose mass over time. Think of it like a bank account where the balance is slowly being drained by small, continuous withdrawals. Over incredibly long periods, this process can lead to the complete evaporation of the black hole. The information paradox emerges from the fact that the particles emitted as Hawking radiation seem to carry no information about the material that originally formed the black hole. According to quantum mechanics, information about the state of a system must be conserved. However, if a black hole evaporates completely, all the information about the matter that fell into it appears to be lost. This contradicts the principles of quantum mechanics, which state that information cannot be destroyed. It's as if you burned a book and then tried to reconstruct it from the ashes. It seems impossible to recover the original content. This paradox has led to intense debates and research, with physicists proposing various solutions, such as the holographic principle or the idea that information is somehow encoded in the radiation itself. One of the most compelling aspects of the information paradox is that it highlights the incompatibility between quantum mechanics and general relativity. These two pillars of modern physics are incredibly successful in their respective domains, but they seem to break down when applied to black holes. Resolving this paradox could require a deeper understanding of quantum gravity, a theory that unifies these two frameworks. Until then, the information paradox remains one of the most intriguing and challenging problems in theoretical physics, driving researchers to explore the very fabric of the universe. Hawking radiation and quantum gravity. Black holes, those cosmic vacuum cleaners, aren't as eternal as once thought. They can evaporate, and this is where Hawking radiation comes into play. This radiation is a fascinating phenomenon predicted by physicist Stephen Hawking, which suggests that black holes can emit particles and gradually lose mass over time. It's a slow process, but given enough time, even the most massive black holes would eventually evaporate completely. This is where the connection to quantum gravity becomes intriguing. At the heart of Hawking radiation is the concept of quantum fluctuations. In the quantum world, particle-antiparticle pairs are constantly popping in and out of existence, like tiny bubbles forming and bursting in a cosmic foam. Normally, these pairs annihilate each other almost instantly. But near the event horizon of a black hole, something extraordinary happens. One particle can fall into the black hole while its partner escapes as Hawking radiation. This process steals a tiny bit of the black hole's energy, causing it to lose mass over time. It's like a cosmic game of tug-of-war, with the black hole slowly losing ground. The gradual evaporation of black holes due to Hawking radiation raises profound questions about quantum gravity. Quantum gravity is the elusive theory that aims to reconcile general relativity, which describes gravity on large scales, with quantum mechanics, which governs the universe on the smallest scales. Black holes are unique laboratories for studying quantum gravity because they involve extreme conditions where both theories come into play. As black holes evaporate, they provide a window into the quantum nature of space-time itself. The information paradox, which questions what happens to the information contained within a black hole as it evaporates, is one of the most pressing issues in this field. Resolving this paradox could bring us closer to a complete theory of quantum gravity, unifying our understanding of the universe. The implications of Hawking radiation and black hole evaporation are vast. For instance, the smallest black holes, if they exist, would evaporate the fastest. This could have significant consequences for the early universe, where such primordial black holes might have formed. Additionally, The study of Hawking radiation could provide insights into the nature of dark matter and dark energy, two of the most mysterious components of our universe. By understanding how black holes lose mass and energy, we might uncover new clues about the fundamental forces that govern the cosmos. The journey to unravel these mysteries is ongoing, and each step brings us closer to a deeper understanding of the universe and its underlying laws. Black hole firewalls. Black holes, those cosmic vacuum cleaners, are not as eternal as once thought. They can evaporate, and this process is known as Hawking radiation, named after the renowned physicist Stephen Hawking. This theory suggests that black holes can emit radiation, slowly losing mass and energy over time. It's like a slow, cosmic fade-out. The mechanism behind this is quite fascinating. Near the event horizon, the boundary of a black hole, particle-antiparticle pairs are constantly being created and annihilated. Sometimes, one particle falls into the black hole while its partner escapes. From an outside observer's perspective, it looks like the black hole is emitting radiation. This process is incredibly slow for large black holes, but given enough time, even they will evaporate. Now let's talk about black hole firewalls. This is a more recent and controversial idea. According to the principle of equivalence, if you were to fall into a black hole, you wouldn't feel any different from falling into a regular gravitational field. You'd pass the event horizon unscathed and continue your plunge into the singularity. But this leads to a problem known as the black hole information paradox. Quantum mechanics says information can't be destroyed, but if it's sucked into a black hole, it seems to disappear. To resolve this, some physicists have proposed the firewall hypothesis. They suggest that at the event horizon, there's a layer of high-energy particles, a firewall, that would incinerate anything trying to pass through. It's like a cosmic border control with a very strict no-entry policy. The firewall idea is still hotly debated. Some physicists argue that it violates the principle of equivalence, while others think it's a necessary consequence of quantum mechanics. It's a bit like a heated argument at a family dinner, but with more math and fewer raised voices. One thing is clear, though, our understanding of black holes is far from complete. They continue to challenge our notions of physics and push the boundaries of our knowledge. It's an exciting time for astrophysics, and who knows what we'll discover next. Maybe one day, we'll even understand what really happens at the event horizon. Until then, the mystery remains, and the debate continues. The role of entropy. Entropy, a measure of disorder or randomness, plays a pivotal role in the fascinating phenomenon of Hawking radiation and the eventual death of black holes. At the event horizon, the boundary of a black hole, quantum effects become significant. According to quantum theory, particle-antiparticle pairs are constantly being created and annihilated in the vacuum of space. In the intense gravitational field near a black hole, one of these particles can fall into the black hole while its antiparticle escapes. The escaping particle is what we call Hawking radiation. This process reduces the mass and energy of the black hole, causing it to slowly evaporate over time. Think of a black hole as a cosmic ice cube on a hot day. The ice cube, black hole, is slowly melting, losing mass, due to the heat, Hawking radiation. The more it melts, the smaller it gets, and the faster it melts. This is because the smaller the black hole, the hotter it becomes, and the more intensely it radiates. The entropy of the black hole is tied to its surface area. As the black hole loses mass, its surface area decreases, and so does its entropy. This is a bit counterintuitive because, in most systems, entropy tends to increase over time. But black holes are unique in this regard. The gradual evaporation of black holes due to Hawking radiation raises profound questions about the nature of information and entropy in the universe. According to the second law of thermodynamics, the total entropy of an isolated system can never decrease. However, as a black hole evaporates, its entropy decreases, seemingly violating this law. This is known as the black hole information paradox. Resolving this paradox is one of the biggest challenges in theoretical physics today. It's a reminder that our understanding of the universe is still evolving, and there's much more to discover. Black hole information loss. Black holes are cosmic vacuum cleaners, sucking in everything that gets too close, even light. But they aren't indestructible. In 1974, Stephen Hawking proposed that black holes can slowly evaporate, a process now known as Hawking radiation. This happens because of a quirk in quantum mechanics. Particle-antiparticle pairs pop in and out of existence everywhere in the universe, even in the empty space near a black hole. If one of these pairs pops up right on the event horizon, the point of no return, one particle might fall into the black hole while the other escapes. The escaped particle is what we see as Hawking radiation. Over incredibly long periods, this process causes the black hole to lose mass and shrink. Eventually, it could vanish entirely. Now, here's where things get tricky. When a black hole evaporates, it takes all the information about the matter that fell into it. Think of it like this. Imagine you're at a library, and someone burns a book. The book is gone, but the information inside it isn't necessarily lost forever. You might be able to reconstruct it from memory or other sources. But with a black hole, it's as if the book burns so completely that not even a whisper of its contents remains. This is the black hole information loss paradox. It challenges a fundamental principle in physics, that information can never be completely destroyed. The paradox arises because, according to quantum mechanics, information must always be conserved. It's like a cosmic accounting rule: what goes in must come out. But if a black hole evaporates, where does the information about the stuff that fell into it go? Some physicists think the information might be encoded in the Hawking radiation, like a faint echo of the black hole's past. Others suggest that the information is somehow stored in the black hole's event horizon, waiting to be decoded. There's even a radical idea that black holes might not evaporate completely, leaving behind tiny remnants that hold onto the information. But these are just theories. Nobody knows for sure. The black hole information loss paradox is a big deal because it highlights a deep conflict between two of our most successful theories: general relativity and quantum mechanics. General relativity describes the large-scale structure of the universe, while quantum mechanics governs the tiny world of particles. They're like two pieces of a puzzle that don't quite fit together. Resolving this paradox could bring us closer to a theory of quantum gravity, a unified framework that explains everything from the smallest particles to the largest black holes. Until then, the mystery remains, a tantalizing clue to the secrets of the universe. Holographic principle. Black holes, those cosmic vacuum cleaners, aren't as eternal as once thought. They can evaporate, and the holographic principle offers a mind-bending way to understand this process. Picture a black hole as a vast, dark ocean. In the void of space, particle-antiparticle pairs pop in and out of existence, like waves appearing and disappearing on the ocean's surface. Near the event horizon, the black hole's boundary, one particle might fall in while its antiparticle escapes. The escaped particle is what we call Hawking radiation. Over time, this process drains the black hole's energy, causing it to shrink and eventually vanish. The holographic principle adds another layer to this. It suggests that all the information within a volume of space can be encoded on a boundary to that space. Think of it like a two-dimensional movie screen encoding a three-dimensional movie. For a black hole, the event horizon acts like this screen. The information about everything that's fallen into the black hole is preserved on its boundary. This is crucial because it addresses a paradox. If black holes evaporate completely, where does the information about what fell and go? The holographic principle offers a solution. It's encoded on the event horizon. But how does this relate to the death of black holes? As a black hole loses mass through Hawking radiation, its event horizon shrinks. The information encoded on it becomes more and more compressed. At the end of a black hole's life, it's a tiny, information-packed dot. What happens then is still a mystery. Some theories suggest the black hole might explode, releasing all the encoded information in a burst. Others propose it might leave behind a tiny, stable remnant. The holographic principle doesn't provide all the answers, but it's a step towards understanding the ultimate fate of black holes and the information they swallow. Black hole complementarity. Black holes, those cosmic vacuum cleaners, are not as eternal as once thought. They can evaporate, and this process is known as Hawking radiation. Picture this. At the edge of a black hole, in the intense gravitational field, particle-antiparticle pairs pop in and out of existence due to quantum fluctuations. Normally, these pairs annihilate each other quickly, but sometimes one particle falls into the black hole while its partner escapes. The escaped particle is what we call Hawking radiation. The black hole loses a tiny bit of mass in this process. Over vast time scales, this gradual loss of mass leads to the black hole's evaporation. Now, here's where things get really interesting. Black hole complementarity is a principle that tries to resolve a paradox that arises from this evaporation process. It suggests that information about the particles that fall into a black hole is not lost forever. Instead, it's encoded on the black hole's event horizon, the point of no return. Think of the event horizon like a cosmic tattoo parlor. As particles get tattooed onto it, the black hole's mass and entropy increase. When the black hole radiates, the information is somehow imprinted on the outgoing radiation. It's like the tattoo gets transferred to the escaping particle. But how this information transfer happens is still a mystery. The complementarity part comes from the idea that an observer outside the black hole and one falling in would have complementary views. The outside observer sees the information in the radiation, while the infalling observer sees it as it crosses the event horizon. It's like watching a magic trick from two different angles. You see the same trick, but the perspective is different. This principle is still a topic of ongoing research and debate. It's a bit like trying to understand a complex puzzle with some pieces missing. Scientists are still figuring out how all the pieces fit together. One of the big challenges is that this process happens over incredibly long time scales. For a black hole the size of the ones we've observed, the evaporation process would take much longer than the current age of the universe. So, we can't just sit back and watch a black hole evaporate to test these ideas. Instead, scientists rely on theoretical models and mathematical calculations. It's like trying to understand how a sandcastle erodes over millions of years by studying the effects of a single wave. You have to extrapolate and make some educated guesses. Despite these challenges, the study of Hawking radiation and black hole complementarity has given us profound insights into the nature of black holes, quantum mechanics, and the fabric of space-time itself. Final stages of black hole evaporation. Black holes, those cosmic vacuum cleaners, aren't as eternal as once thought. They can evaporate, and when they do, it's a slow, dramatic process. As a black hole loses mass, it shrinks, and its temperature rises. This is because the smaller the black hole, the more intense its gravitational field, and the hotter it gets. It's like a tiny, ultra-dense star, but without the fusion. The final stages of this evaporation are particularly fascinating, as the black hole approaches its end. Picture this. Near the event horizon, the boundary of a black hole, space is a bubbling cauldron of quantum activity. Particle-antiparticle pairs pop in and out of existence all the time, a phenomenon known as quantum fluctuation. Normally, these pairs annihilate each other quickly, but sometimes one particle falls into the black hole while its partner escapes. The escaped particle takes away a tiny bit of the black hole's energy, causing it to lose mass. It's like a cosmic game of catch, where the black hole always loses. Over time, this process accelerates. The black hole loses mass faster, its temperature soars, and it becomes a furious, tiny fireball. As the black hole approaches the end of its life, it's a whirlwind of activity. It's no longer a silent, dark giant. Instead, it's a chaotic, energetic spectacle. The black hole's mass plummets, and its temperature skyrockets. It's like a dying star, but without the beautiful explosion. The final stages are a frenzy of particle creation and annihilation. The black hole is a tiny, ultra-hot, ultra-dense nugget of energy, desperately trying to hold on. But it's a losing battle. The evaporation process is relentless, and the black hole's end is inevitable. In the very last moments, the black hole is a tiny, ultra-hot speck, barely holding on. It's a mere whisper of its former self. The particle-antiparticle pairs are created and annihilated at an incredible rate. The black hole is a frenzy of energy, a tiny, chaotic storm. And then, in a final burst of energy, it's gone. The black hole has evaporated, leaving behind only a faint echo of its former self. It's a dramatic, spectacular end to a cosmic giant. But don't worry, this process takes an incredibly long time. Even the smallest black holes take billions of years to evaporate. So, we're safe for now. Implications for the universe. Black holes, once thought to be eternal and unchanging, are now understood to have a finite lifespan due to a process called Hawking radiation. Proposed by physicist Stephen Hawking, this theory suggests that black holes can slowly lose mass and energy over time, eventually evaporating completely. This phenomenon has profound implications for the universe, challenging our understanding of its ultimate fate. At the heart of this process lies the quantum mechanical concept of particle-antiparticle pair creation. Near the event horizon of a black hole, these pairs of particles can pop into existence due to the intense gravitational field. Normally, these particles would annihilate each other almost instantly. However, if one particle falls into the black hole while the other escapes, the black hole loses a tiny amount of energy. This escaped particle is what we call Hawking radiation. Over vast stretches of time, this gradual loss of energy causes the black hole to shrink. As it loses mass, the rate of Hawking radiation increases, leading to a runaway process where the black hole evaporates more and more quickly. This means that, given enough time, every black hole in the universe will eventually disappear. The smallest black holes, if they exist, would evaporate first, while supermassive black holes at the centers of galaxies would take an unimaginably long time to fade away. This process raises intriguing questions about the ultimate fate of the universe. If black holes can evaporate, what does that mean for the matter and energy they've consumed over billions of years? Will the universe eventually be left with only radiation, or are there other factors at play? One of the most fascinating implications of Hawking radiation is its potential to bridge the gap between quantum mechanics and general relativity. These two pillars of modern physics have long been at odds, with quantum mechanics governing the very small and general relativity describing the very large. Hawking radiation, however, is a quantum mechanical process that occurs in a strong gravitational field, making it a prime candidate for studying their interplay. Understanding this process could lead to a deeper, more unified theory of physics. Moreover, the evaporation of black holes could have significant consequences for the large-scale structure of the universe. As black holes disappear, the galaxies they anchor might be destabilized, altering the cosmic web of matter that we observe today. This could reshape our understanding of galactic evolution and the distribution of matter in the universe. The implications of Hawking radiation extend beyond theoretical physics. They touch on fundamental questions about the nature of reality, the arrow of time, and the ultimate fate of the cosmos. If black holes can evaporate, it suggests that nothing in the universe is truly eternal, not even the most massive and seemingly indestructible objects. This idea challenges our notions of permanence and invites us to consider a universe in constant flux, where even the most stable structures are subject to change. As our understanding of Hawking radiation deepens, so too will our appreciation for the dynamic and ever-evolving nature of the universe. Future research directions. Black holes, once thought to be eternal and unchanging, are now understood to have a finite lifespan due to a process called Hawking radiation. This phenomenon, proposed by physicist Stephen Hawking, suggests that black holes can slowly lose mass and energy over time, eventually evaporating completely. The process involves the creation of particle-antiparticle pairs near the event horizon, the boundary beyond which nothing can escape a black hole's gravity. One particle falls into the black hole, while the other escapes, carrying away energy. This gradual loss of mass means that black holes can eventually disappear, a concept that has profound implications for our understanding of the universe. Future research in this area is likely to focus on several key directions. One is the search for experimental evidence of Hawking radiation. While direct observation is challenging due to the extremely low temperatures and energies involved, scientists are exploring indirect methods. For instance, they might study the behavior of black holes in the early universe or look for signatures of Hawking radiation in the cosmic microwave background. Another avenue is the study of quantum gravity, the theory that aims to reconcile general relativity with quantum mechanics. Understanding quantum gravity is crucial for a complete description of black hole evaporation and the information paradox, which questions what happens to the information about the physical state of objects that fall into a black hole. Theoretical work will also continue to explore the nature of black hole evaporation. For example, researchers might investigate whether the process leaves behind any remnants, such as Planck mass particles or other exotic objects. They could also study the role of higher-dimensional theories, like string theory, in describing black hole physics. These theories suggest that our universe has more than the familiar four dimensions of space-time, and they might provide insights into the final stages of black hole evaporation. Additionally, scientists might explore the implications of black hole evaporation for the large-scale structure of the universe. For instance, they could study how the disappearance of primordial black holes might affect the distribution of matter and energy in the cosmos. Another exciting direction is the study of black hole thermodynamics. This field applies the laws of thermodynamics to black holes, treating them as if they were physical systems with temperature and entropy. Hawking radiation plays a central role in this framework, as it allows black holes to have a well-defined temperature. Future research might focus on understanding the microscopic origins of black hole entropy, which is thought to be related to the number of ways that the information about the black hole's interior can be encoded on its event horizon. This could provide a deeper understanding of the connection between quantum mechanics, gravity, and information theory. So, to wrap up, imagine a black hole as a cosmic iceberg, slowly melting under the heat of its own energy. Just as a pair of ice skaters, our particle-antiparticle pairs, might spin away from each other, so too do these particles near the event horizon. One escapes, stealing a bit of the black hole's energy, while the other falls back in. Over time, this process, known as Hawking radiation, causes the black hole to lose mass and eventually vanish, leaving behind only the echoes of its once mighty presence. In simpler terms, black holes aren't as eternal as we once thought. They can evaporate over time, shrinking and fading away like a whisper in the wind. This mind-blowing idea, proposed by the brilliant Stephen Hawking, reminds us that even the most mysterious and powerful objects in the universe aren't immune to the passage of time. Now, we'd love to hear your thoughts. Does this idea of black holes slowly fading away fascinate you as much as it does us? Let us know in the comments, and don't forget to like and share this video if you enjoyed it. And hey, if you're hungry for more cosmic mysteries, make sure to subscribe to our channel. Next time, we'll be diving into the enigmatic world of dark matter. Trust us, it's a journey you won't want to miss. Until then, keep exploring, and remember, the universe is full of wonders just waiting to be discovered.